slide is about the same thing as what we discussed just now, the temperature profile. During daytime, the temperature profile is nearly uniform with height over most of the middle of the ABL. That means it doesn't change with height that much. Near the bottom is a surface layer with a super adiabatic temperature gradient. Super adiabatic means the temperature profile is very unstable. The temperature at the ground is hot, while the temperature above is a lot colder, so the gradient is very large. Super adiabatic, as required to cause a positive heat flux. So when, of course, when the temperature gradient is very large, when the slope is very large like this, then there's a lot of heat flux being removed from the ground, and that means that there's a lot of mixing. So near the top is the statically stable capping inversion, which during the daytime is called the entrainment zone. Above that is the free atmosphere, illustrated here with the statically stable standard atmosphere. So this is about the same as just now, except for it has a bit more detail. Here is the temperature profile. Okay, these two here, temperature profile. And you've seen this in the previous two slides. But this is during the day. This is for humidity, and this is for velocity, wind. So this one, ignore this part here first. Just consider this T and temperature. Notice the profile. But I already talked about that in the previous slide as well. Now, at night, a second stable layer called the stable atmospheric boundary layer or the nocturnal atmospheric boundary layer forms near the ground, like what we saw just now, in response to the cooling of the air by the radiatively cool surface. So above, the capping inversion formed the previous day is still present. So there's the residual layer there. The stable boundary layer near the ground consumes TKE. TKE stands for turbulent kinetic energy. That means turbulence. The stable boundary layer suppresses turbulence, resulting in weak and sporadic turbulence there. Sporadic means once in a while. It happens and then it stops happening for some time and then suddenly it happens again. So turbulence is there, but it doesn't happen so often. So between these two layers is the residual layer. Remember, the mixed layer changed to a residual layer, which contains dying or zero turbulence and also the residual heat, moisture, and pollutants that were mixed there during the previous day. So the residual layer is something like a reservoir or a place where they store all this moisture and so on throughout the day. So from day to night and day again. So you can imagine like during the day, it starts to evaporate, mix into the atmosphere, and then at night it contains inside the mixed layer because of less turbulence. Then during the day it starts to evaporate again and then contains in the mixed layer and so on. Instead of moisture, it could also be pollutants as well. So notice the profile is this profile, these two parts. And this is something we discussed just now in the slides just now. Now, humidity. Just now was temperature, now it's humidity. So during the daytime, one thing to focus is these two, this one and this one. During fair weather, the free atmosphere is relatively dry because of the subsiding air in anticyclones or the highs. So evaporation from the surface during daytime adds moisture to the boundary layer. That's what we discussed just now. The net result is that there is a rapid decrease of specific humidity with height in the surface layer. So where does it show? So during the daytime, humidity decrease, rapid decrease, as expected by the bulk aerodynamic formula to drive moisture fluxes from the ground into the boundary layer. So from the ground, high moisture content. Why? Because there's water on the ground. There's water coming from the plants compared to somewhere above. So here high concentration, here low concentration. The ground high, above low. So of course from high moves to low quite quickly as well. So you can see this rapid change. So that process adds moisture from the ground, causes the mixed layer to be more humid than the free atmosphere air aloft, and leads to a humidity jump across the capping inversion. Because of this very high speed addition of humidity, it will increase the concentration here. The concentration of water in this layer, but then in the free atmosphere is another layer. It doesn't mix, remember? So this is relatively a lot higher than the free atmosphere. buildup of humidity within this layer. Now at night is this one. So at night, looking at this, ignore that, that one's during the day, this is during the night. So at night, humidities in most of the middle and top of the boundary layer do not change due to turbulence because turbulence has diminished. So however, the radiatively cool surface can cause dew or frost formation, which reduces humidity in the very bottom of the boundary layer. So let's take a look. Separate, this is high. In the atmosphere is higher because of during the day. During the day it evaporates and it is contained in the atmosphere. And the surface is low. So notice that this is like this. The slope is positive, while this one, the slope is negative. Notice the difference? Day is like that, and night is like that. Because of this fact, on other occasions, when dew or frost do not occur, specific humidity is relatively uniform throughout the bottom and the middle of the boundary layer. So let's say if there's no water on the surface, then it's about the same. So the summary is that during the day, it evaporates, it accumulates here. At night, this humidity is still there, left over from the day. But then it doesn't come from the ground anymore. Now, wind. During the daytime, drag, now we focus on this right panel for day and night. So drag at the ground, during the daytime, drag at the ground always causes the wind speed to be reduced, while aloft, above, the winds are stronger. So that happens throughout the day and night. So let's look at this graph. You see here, winds are 0. We always assume, even though the winds are very strong, if it's at the ground, 0. Because of this no-slip condition. That means the ground doesn't move because of the wind, right? So the wind definitely is 0 at the surface. So at the bottom, it's 0. And as it moves away from the surface, it becomes stronger. This is for day, and at night, it's also the same. 0, stronger, somewhere above the surface. But you can see the degree is different between these two. But I mean, this is for night. Now it's still during the day. Now, turbulence communicates drag from the ground throughout the middle part of the mixed layer during daytime, resulting in homogenized uniform wind speed with height that is slower than geostrophic, subgeostrophic, and which crosses the isobars at a small angle toward lower pressure. So there's drag here. So there's turbulence here. This turbulence carries the drag from the ground to the mixed layer. And once it reaches a certain height, then it's homogenized. Same goes for this one, except for there's a slight decrease here. But notice that it's homogenized here. This means that somewhere in the ground, the winds are very what do you call it? It changes a lot. But if you go further up, aloft, and you notice that the winds are more or less stable at a certain value. But on the ground, it's varies by quite a bit. But the bottom point is that the drag is carried into the upper layer through turbulence. If it's very smooth, then drag is less. I mean, there is less contribution of drag in the upper layer. If it's very rough, like an urban area, then there's more contribution of drag in the upper layer. So above the capping inversion or the entrainment zone, so somewhere here is the capping inversion or entrainment zone, or sorry, somewhere here, wind quickly recover to their full geostrophic value. So geostrophic is actually those large-scale winds that are above. Winds that are created due to the spinning of the earth, created through the difference between surface conditions, between land and ocean. So those are really strong winds above, like say about 2 kilometers, 3 kilometers above the surface of the earth. Because there's no turbulence there to communicate surface drag information. There's no drag, so it's the highest, it's at its highest value. Thus, wind shear tends to be concentrated in both the surface layer and the entrainment zone. Remember wind shear, those drags? The most effect of shear would be somewhere here. Sorry, this is night. Somewhere here, because there's a difference. Here, what do you think of the wind shear? Is it large? The wind shear here. Look, is it on a gradient? No, right? It's just vertical. So that means basically no wind shear. But over here, high wind shear. So then you have another layer, high wind speeds here, low wind speeds here. So there is another wind shear here. So one wind shear level and one wind shear here. So that's what it means by that one. The wind shear tends to be concentrated in both the surface layer and the entrainment zone layer. So you can imagine there's turbulence here. There's also some turbulence here. Why? Because of the difference in wind speeds in regions. So here is different wind speed, here's different wind speed, here's different wind speed, here's different wind speed. Now we go to nighttime. So at night, you can compare between daytime and nighttime. The suppression of turbulence by the stable boundary layer causes the air in the residual layer to suddenly be frictionless. So where's the residual layer? Here. This residual layer air accelerates towards geostrophic, but due to the Coriolis force, there's a Coriolis force because of the spinning. At night, there's this effect of Coriolis force, but due to the Coriolis force, undergoes an inertial oscillation in which the wind vector oscillates around the geostrophic wind. So what is going on here? So here, we see about the same trend as during the daytime, but there's a lot more variation there. Here, reaches a stable value here. Up to this point here, it's no longer, because of that situation just now, this is due to the large-scale process, the Coriolis force. So the winds become faster than geostrophic, super geostrophic during a portion of the inertial oscillation, causing a low-level wind speed maximum, or this nocturnal jet or low-level jet. And this actually is a lot higher, if you notice, a lot higher than this. You think that this is the highest, right? Somewhere above is the highest wind speed. But there is a portion in the residual layer where the wind speed is a lot higher than the geostrophic wind. Okay, there is a contribution here. There is a contribution here. Because of this added contribution, it increases this point here. That's what it means by the winds become faster than geostrophic during a portion of the initial oscillation. One is pushing, the other is pushing. Both is pushing like you're on a swing, and then one is pushing and the other is pushing at the same time, and it pushes that one even further away. The swing further away. So this is the effect of this and this too. So there is at night, there is a low-level jet, which is much stronger than the geostrophic wind. Meanwhile, closer to the ground, the winds become nearly calm. Here, notice, nearly calm, 0. Because the air is affected by drag at the ground, but is no longer subject to turbulent mixing of stronger winds from aloft, because turbulence has diminished. So that's the reason why at night winds are usually very low, because there's no more effect of turbulence from above.